Today we shall learn about Hamilton's principle. Remember that we arrived at D'Alembert's principle. The way we have wrote it down last time is that I have this delta W virtual work done, and this is because of all external forces. And then we consider this term, which you can write as summation over I equals 1 to n f inertial I and then delta qi equals 0. D'Alembert's principle tells you that this will be equals to 0. So this I can cast the exact same equation in a little different form. I can define the entire thing as delta W prime because I have this delta W which I already had in the previous line, and then I define this quantity. This is just for the sake of understanding. I call it the virtual work done because of the inertial forces. So this is for external or sometimes called the imposed forces, and this is by the inertial forces. And believe me, and you must have done already earlier in one of your courses, that using this principle you can get to the Euler-Lagrange equation. So one can go to find the Euler-Lagrange equations. So this is what we left at the last discussion, at the end of the last discussion. This is where we were. So let us carry forward from there. So remember that I have this total virtual work done. One is coming from the external force, the other is coming from the internal forces. And okay, so you can write this way. So let me write it this way, the plus sign. So obviously delta Wi is minus of this entire thing, minus of summation I equals to 1 to n Fii delta Qi. The D'Alembert's principle, then I can just cast in this term that delta W prime equals to 0. So that becomes a D'Alembert's principle in these notations. And just let me remind you what was delta. So delta was, you remember, is coming from okay, so this is coming from virtual displacements. Okay. Now it turns out that when one discusses Hamilton's principle, one uses a different delta, which is nothing but the small delta, which I by mistake used it here once. I was supposed to use a capital delta for all things that are virtual, but by mistake I have used it there already. And from now on what I will do is I will just change all these deltas to the small delta, and this is just a notation thing, and one used to follow the notation which is there in the literature mostly. So I will call the small delta as the virtual displacement. So I have it once more here, so I will just change that also. So let us carry forward and try to see what is happening here. So meaning of the D'Alembert's principle. Sometimes you will see that it is easier to describe things in the original three-dimensional Cartesian coordinate systems. So what I will do is I will draw two pictures here. So one will be in the generalized coordinates, which is obviously small in dimensional, and the other will be in the Cartesian system, which is three-dimensional. And what I am drawing here are not the trajectories. This is just a kind of cartoon picture. So if I say a point here, this is a point in n-dimensional space. When I draw it here, so this corresponds to n points, capital N number of points in the three-dimensional space. So what I am doing with this point, I will say that this is my initial point. So the system is here. Okay. So this here I will denote that initial point by Qi. Here I will denote the initial point by capital Xi. So X is a vector which has x1, y1, z1. If I choose I, small I equals to 1, etc. Okay. So here I have small n of them. Here I have capital N of them. The motion here is a restricted motion because you see that it's the original Cartesian coordinate system. So I don't have the constraints imposed already. So if I draw anything in the right hand side of this, those drawing has to follow all the constraints that I have. Here in the left hand side, because I am doing it in the generalized coordinate, the motions are not restricted. You can move arbitrarily in this coordinate. So now if I tell you what is Qi, which basically telling me what is this point, that does not tell me anything about what is the point that I can go in the next time instant. Okay, so what I have to choose here is the time derivative of Qi, obviously n of them again, and correspondingly here is the velocity, right? So this is configuration space and the Cartesian space velocities. And why do I need to choose the velocity? Because I know qi at t. So if qi at t plus delta t, qi at t plus dt is nothing but qi at t plus qi dot dt. As I said, so this is my choice. So I choose any velocity, and once I choose a velocity, I go to another point. Now, obviously, depending on my choice, so if this is my choice 1, my choice 2 may land me up there. So you can see it's a different point. The direction and the amplitude both are different. So you may have moved by a different amount in a different direction because the components of qy's are different. And so say these are all the possibilities. I can go there, 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 I can go there. I have no idea where I can go. So these are all the possibilities where I can go if I choose arbitrary values of qi dot. And the similar thing here, it will be like that. And just to remind you that it is restricted, I am drawing it only one part, and you can assume that in the right hand side, so this is where it is restricted, so you cannot go there. So now the question is, you want to figure out what is the trajectory using the D'Alembert's principle, and the D'Alembert's principle is supposed to tell you the next instant where the particle is supposed to be. And what is the D'Alembert's principle? Let me write it here. So I have delta omega plus delta omega I, which is 0 for the trajectory. What happens is that out of all this infinite amount of choices that I have for qi dot, if I choose one particular one, maybe this one, then along this path, for this very small amount of change, so this is a special one for which the change that you get because of the change, so let's say that your original imposed forces are monogenic, so I can write this in terms of a potential function, derivative of a potential function. So there is a potential function, so which means what I do is, once I go from this point to this point, that potential function changes. Delta w is not 0, but this thing, which is delta wi, changes just equal and opposite amount, such that they two, when you add up, becomes 0. So that's how you get the trajectory of the particle. If you wish, that is the exercise now that you have to do to figure out where will be the particle at the next time instant. And if you do the same exercise starting there, again there will be many possibilities where you can go, but it will turn out that there is one possibility for which your total virtual work done will be 0, and that will correspond to the trajectory. And you can see that you can now trace out the trajectory of the particle this way. So this is how D'Alembert's principle works. So let me remind you what is delta wi, and you see that this is why I am writing it in terms of Cartesian system, because it is easier to write in terms of Cartesian system. So what is delta wi? So remember that it is I equals, I can write it this way, 1 to n, and this is my force in the Cartesian system. Now I write with a vector, so it has all three components, and this is not just phi, this is this I, and that is given by minus of mass times acceleration, right? So I have dot product of dy dot with delta xi inside that summation. So that's my delta wi. So we realize how the D'Alembert's principle works. Now when you get to the D'Alembert's principle, if you remember that we used Newton's laws and did not derive D'Alembert's principle, so to say, but we arrived at the D'Alembert's principle. Then we said that we will not use Newton's laws in force, we will just use D'Alembert's principle as our starting point for the mechanics. And here today we are trying to find out yet another principle. We will call it Hamilton's principle, and we are trying to get to it using the D'Alembert's principle, if you wish. So what is the problem with this principle? As we said last time, that this principle is in such a form which we cannot say monogenic. What do I mean by that? Well, we said we want to represent the dynamics of the system using one scalar function. So what is the problem with D'Alembert's principle? Well, I have this delta of w prime, which is a sum of the delta w, the virtual work coming because of the external forces, plus the virtual work coming because of the inertial forces. And it turns out that even if I can write this in terms of a monogenic form, so this turns out to be delta of u, so this can be derived from a u, if you wish, a work function, this cannot be, because you see that it is the acceleration, it's essentially the acceleration of different particles, so that cannot be derived, which means that this cannot be written in terms of a scalar. So that scalar gives you the genesis of the dynamics. The dynamics cannot be written in a monogenic form because I don't get that scalar. So what Hamilton did, he observed that when I am going from this point to that point, and for the right trajectory, so that's what we draw using the D'Alembert's principle a while ago. So we said that you can figure out like these small segments at each infinitesimal time intervals where to go starting from here using the D'Alembert's principle. And for each of these infinitesimal time segments, your delta w prime, so say this is the delta w1, in the next time segment you get delta w2, in the next time segment you get delta w3, etc. Each of them are equals to 0, right, by D'Alembert's principle. Hamilton said that I will see the trajectory from one time instant to the other time instant, so from t1 to t, and what I will do is, this trajectory I can see as a summation of all these small delta w segments. We have seen for each of these delta w segments, delta w prime is 0, so this must be also 0 for the entire trajectory. And now I can change the principle. So let's say that the initial time is ti and the final time is tf. Qi corresponds to the initial and qf corresponds to the final position of the system. What I will do is, I will choose any arbitrary trajectory, and for that trajectory I will calculate this integral. And this trajectory, so let me write it here, some f dt, depends on the trajectory. We'll give it a more concrete form, but let us first understand it. So I'll calculate this integral. In fact, this integral is called action integral. So we calculate this integral and s for an arbitrary path. Obviously, the value of s will depend on the trajectory now. What is s essentially? So if you see here, what is f essentially? So f is essentially w prime, if you wish, but it is not equals to w prime. What it is, that is what we will find out. But we say that there is something for each trajectory which I can put in here and calculate the action, calculate this integral value. For each trajectory I will get an integral value, and we know if this is w prime, what happens to the trajectory where I am in. For that trajectory, w prime will have a certain value. So it will not be 0. The integral will not be 0. But then if I do this, if I calculate delta s, and this again I will show you explicitly. Okay, probably I will ask you to prove, but I will tell you why, how to do it. So if I do delta s, that will corresponds to delta f times dt, or f, as we said, is like omega prime, so delta omega prime dt. So which means the actual trajectory, actual path that the particle will follow has a stationary value of this s. Okay, what do I mean by a stationary value of this s? I mean that if I change the trajectory, then s will either increase or decrease. If I change the trajectory, if I start with this blue line, and whatever I change this blue line is supposed to be the actual trajectory that the particle will follow. And if I change this blue line by arbitrarily small amount, and whatever change that I will do, all those changes will be either positive or all those changes will be either negative. So it is just like when we are describing the potential function, we had a stationary point, an equilibrium point, as a minima or as a maxima. So when it is a maxima, whatever change I can do from that point here, it will always, Vx will always decrease. Whenever I am in a minima, whatever change I will do, Vx will always increase. Similarly here, we are saying that we are in that particular blue line, which is the actual trajectory that the system will follow. Whatever change I do from there, the value of this action will either increase or decrease. Now, this is a little different mathematical problem, mathematical form than the functions, and let us discuss that a little bit before we go ahead. instead of a normal analysis, real analysis that we do for doing, which we call calculus also, for doing all these things, we now are in the realm of functional analysis. So one particular functional analysis that we are doing, and here let me define. So this part has nothing to do with the D'Alembert's principle or the trajectory of the particle. This is just a little bit of mathematics that we need to know at this point of time. Probably you have studied it in your math courses, but let me still do it. So I define this integral of the function fx over x. It's a definite integral. It's from x1 to x2. And you will say that, well, it will have a value a. It's a number. So this must be a number, right? Now, what I do is, so I calculate this, the same integral, but now for a different function, gx. What do you expect? I will still get a number, but now it will be a different number, which corresponds to that function. You see what I am getting to. I am keeping everything else fixed. I am still doing x1 to x2 integral over dx. Okay. So the value of a depends on which function I choose. So this is called a functional. A is called a functional. So that's what I mean. So now I can define derivative of a functional. What if I change fx a very small amount? So let's change fx, change the function f as a function of x. So when I say change fx, I basically change the functional form by very small amount. What do I mean by that? Well, let me draw one fx for you and give an example. So say this is, I am drawing fx, and say this is the curve. In the same plot I draw gx, and gx looks like this, which means that these two functions are almost same. They deviates a little bit. Gx, or the change fx, so let's call that f bar x. It will be almost fx, and then there is a little change in it, so I denote it by phi x. But remember that the change has to be little, so I multiply it by epsilon to make sure it is little. I say epsilon is very small. So if I now ask what is the functional derivative of f, that is what I write as delta f, and this is by definition is f bar x minus fx, and you see what it is, epsilon phi x, right? So let me keep it there. Delta of f is epsilon phi x. Remember, what does delta of f means? It means what is the change in the function f as I go from fx to gx. So that is that delta, that small change. If I just go back and put it into perspective in terms of our trajectories, so this, you remember, is, we said, is the actual trajectory. So the particle is moving this way. So when I say a little bit change from that, so again I mean that it's almost follow that line, and then there is a little bump there, if you wish. So that little change here can be the delta of this trajectory. Now just also let me remind you what is df. Df is the differential of f. This is not the functional derivative now, this is the analysis, the derivative of a function. This you know what it is. So this is fx plus h minus fx. So that is usually you define where h very small. So once you have done these two, so let us ask the question, what is, say, delta of df? So how do I calculate? I know that what is df. Df is coming from there, df is f of x plus h minus fx. So I can just replace it for df. Then I get delta of, okay, so I am assuming that they are associative, so you can just separate them out. So I get delta of this minus delta of fx. Okay. So what is delta of fx plus h? Well, delta of f is epsilon times phi x. So this should be epsilon times phi x plus h. And delta of f is just epsilon times phi x. So what you get at the end of the day is epsilon times phi x plus h minus phi x is nothing but d phi. Right? That comes again from the same definition of df. That you know, that is the usual analysis technique. Can you calculate now d of delta f? Well, that turns out to be even easier. So I say d of what is delta f? Delta f is epsilon phi x, and epsilon is a constant, so this can just go out of the differential. So it's just epsilon d phi x, and you realize that these two are same. Now I'll not prove, but leave it for you to prove. You can use the exact same arguments to show that these two integrals are also same if we calculate them over the same path. These two will be very useful for us. Now let us come back to our original problem. What is the original problem? I want to calculate this integral over different paths. And for the right trajectory of the system, at least from D'Alembert's principle, we know that this will be equals to 0. We shall use all the things that we have learned about the functional calculus to calculate that thing and see if we can bring it to a monogenic form. So remember that we had delta of w prime. Now I have written the right delta equals delta of w minus delta of w inertial, and this is supposed to be 0. So this is D'Alembert's, and then in the Hamilton's form this becomes, you are doing the integral between t1 and t2 and delta of w prime t1 to t2, and let us for the time being assume that we have a monogenic force. Always you start with the cases where you know it works. So D'Alembert's principle works for a monogenic force, so we assume a monogenic force to start with, which means I can write this as delta of, that is coming from delta w, and I have the other term which I can write as, I write this in Cartesian. Why I write this in Cartesian? We have written the acceleration already in Cartesian here. This is delta wi we had written in Cartesian, and the reason we have written it in Cartesian is because we know how to write it in Cartesian. We actually have not figured out how to write the same thing here, and I request you to try to do that. It will involve those metrics, because I'll not tell you why, and it's not very straightforward. We know how to do it obviously, but it is not very straightforward, and we need to know a little bit of sophisticated mathematics before we can do that. And it will suffice for us if we can write this down in Cartesian for this particular example. So I'll just do that. There is no harm in it. And remember that I will get a minus sign here instead of a plus sign, because delta wi was minus of the force. I equals 1 to n, and I am writing in vector notation. You see that we are going backwards, the inertial and then delta etc. What happens to the first term? Well, the first term I can just write as delta of t1 to t2 and then udt. You see that's what we have written here. So I have just used this. We had delta of udt here, and I just took the delta outside. As I said that you should be able to prove this, so that's your homework. You should be proving this integral relation. So this is straightforward. We have to work out this integral. So let us call this integral as I2. Okay, I1 we have already calculated. This is I1. So let's calculate I2. Calculate means here is to keep it in a form which will be useful. So I have this summation over I equals 1 to capital N, and then F inertial. F inertial I is nothing but mass times the acceleration. In fact, we defined F inertial I that way. So this is bi dot delta xi. So I have not done much here up to this point. Now I'll do a trick. What I'll do is, I want to make this, let's calculate this quantity ddt of mi bi dot delta xi. What will it be? Two functions multiplied. First take the derivative of the first function, so mi bi dot, keep the second function untouched, and then keep the first function untouched, so kill them one by one basically. So this is ddt of delta xi. So mi vi dot delta xi. You see here I have d of delta, and that we have proven that d of delta is same as delta of d. So I can just write this d of delta in terms of delta of d, so which means that this is mi vi dot delta of dxi dt is nothing but vi. As you can see, this term that I am writing right now is something that already exists in inside our integral. Now can we write this term? See, we have already seen that the functional derivative which comes with the delta behaves almost like the original derivative. So I can just write this as half of mi delta of vi mod square. So what happens if I do delta of vi mod square? Well, vi mod is nothing but vi dot vi, so I get 2 vi dot delta vi. But I have vi dot delta vi here, so I put a half to compensate for that. And you will agree if I do the next step. Mass is a constant, as we said, it describes the particle. There is no way you can change it, so I can just bring the delta outside. So for all the trajectories, the mass of the particle will be the same, right? So it doesn't matter which path the particle is following. If you look at this integral, I have this term in the integral. which is essentially this term. So I can write this term as this term minus that term. But when I write this as a minus term, that kills this minus, it becomes positive. So let me write down I2 for you, and then we can check if we have written it properly. So I2 now becomes positive, so it becomes T1 to T2. Okay, so I am replacing this, which is this, as this minus that. So let me first write this term. That will come with a minus sign. And that's it, because see, it's ddt, and I have a dt over here, so that dt cancels out. So it becomes a total differential essentially. And the second term becomes positive, because when I replace this with this minus that, so this term comes with a minus sign, which kills that minus. So what do I get in here? T1 to T2 delta of summation over I equals 1 to n mi bi mod square and then dt, which is, this integral is easy to do because it's the total differential. So the integral is this itself, evaluated at T1 and T2. So let's give the minus sign over here. Plus, what is this quantity? Well, all of you agree this is nothing but a kinetic energy of the particle. And as always, I can take delta outside, that I have shown you at least twice now. So that's I2. And let's bring in I1 and write down the total integral. So the total integral is now this term, delta of T1 to T2 T plus U. Now let us go back and ask the question, what is this total integral? So it's this integral that we are doing, and we call this delta A, because remember that A is, we called the action. So this is what we defined as our action. This is something that depends on which path you are choosing to explore. So here, where am I? Here, these are the different paths, right? And as we said for the functional analysis discussion, that A will be different for different paths. They depend on which path you are. And we are asking how much is the change if I go from one path to the other path, or two very close by paths. Okay, and that is what is delta A. Where am I? Yeah, here. So that is what is delta A, and A is called the action. So this integral that we have written down here is nothing but delta A. And now it can be done different ways at this point, and we choose one particular way. We choose the case where at the time T1 and T2, the configuration of the system is known. So at the two endpoints, at T1, you know that the system is at, if you wish, in xi in Cartesian or qi, and I write initial in for initial in both the cases. And at t equals to T2 in Cartesian, you are here. And what does it mean? This is delta xi calculated. So if I write this out, I will have delta xi calculated at T2 and delta xy calculated at T1. But those are 0 because I have no variation. So variation is what we call delta, right? So variation is the difference between different paths. At these 2 points, the paths are fixed. You know where the system is, so you cannot change at those two points. So which means this quantity is 0. Evaluated at T2 and T1 is 0, because this evaluated at T2 and T1 is 0. And remember that we had U as minus V, U being the work function, V being the potential. So which means delta A now becomes delta of T1 to T2, T plus U becomes T minus V, and then integrated over time. And this quantity, you can think of this as excess kinetic energy over the potential energy. We call it the Lagrangian of the system. So it's written with L, as you all know already. What is it a function of? Well, remember that V was a function of Q, all the Q's. So it's function of Qi. You can also write in terms of X, and we will discuss that shortly. Kinetic energy is function of the derivative of the coordinates. So it should be Qi dot. And as we promised that in general, you can deal with non-monogenic forces also. So forcefully I say that it is can be a function of time also, and that is the mathematical statement of the Hamilton's principle. Okay, so Hamilton's principle. So let me write it here. What did we do? What we did was that we used the D'Alembert's principle to start with, and then we came to a different understanding where we said that I have this scalar function. So this is a scalar, right? There is only one function that you have to specify, whatever may be the dimension of the space that you are looking at. So L is a scalar function of qi dot and t in general. So I have this scalar function. Now qi is the position of the particle at a given time. At different positions it will have different values, so it's actually a function of t. So is qi dot. So these are function of time. That's why you have the integral over time. And then if I integrate it over t1 to t2, this I called action for the trajectory delta A equals 0. That is the Hamilton's principle. And remember that delta is the functional derivative. You see, we have bring D'Alembert's principle to a monogenic form already. The entire trajectory, entire problem is now solved by knowing this single scalar function called the Lagrangian genesis of the trajectory. So this gives me gives the genesis of the trajectory. And when I consider now Hamilton's principle, I don't come through anything else. What I say is that for a given system I can define a Lagrangian. Okay, how I define the Lagrangian, we are not addressing that question now. That prescription may change system to system, but for a given system we say that we can define a Lagrangian. I integrate the Lagrangian over different paths from a fixed point in time t1 where the configuration of the system is absolutely known to a fixed point in time called t2 where the configuration of the system is absolutely known. For the right trajectory, delta A will be 0. For the right trajectory, A will be stationary. So as we said, that if we change the trajectories a little bit, whatever way we wish, if I am already in the right trajectory, then all the changes either will be positive or all the changes will be negative. Okay, think about it a little bit, so it will be more clearer to you. So how this q depends on t, or q dot depends on t, is the trajectory. So those dependencies will give you different A. So A is a functional of qi as a function of t and qi dot as a function of t. Okay, so this is Hamilton's principle, and now you take this as a principle. I telling you again and again, I am not saying that L is t minus v anymore. That will be the case for the kind of systems that where v exist and monogenic forces and all. But I can come up with a more complicated system where I can define the Lagrangian, but I may not have explicit form of v, or v is not a q dependent only, it's q dot dependent, and as we said, all sorts of problems may arise. But we can say that, well, I don't know what is t and v separately, I just write down the Lagrangian, and Hamilton's principle should give you the trajectory. Okay, now how do I get the trajectory? So I'm still telling you this gives you the trajectory, but how do I get the trajectory? Well, let's see how do I get the trajectory out of it, and that will be the last thing that we'll do today. So remember that L is a function of, and let me for the time being write only these two. It's your homework to put back time over there, so I'm not writing L as an explicit function of time for the time being. You should treat it as an explicit function of time also, and see what happens. What is the result if it's an explicit function of time? What will change from what I'm doing right now? Now, as we said, that the functional derivatives almost follow, I say almost, the rules of the normal derivatives, differentials. So without proving this, let us calculate what is delta of L in terms of qi and qi dot. So you see, basically what you are saying is that L is a function of qi and qi dot. So if I say delta of L, there can be changes in L, functional changes in L because of functional changes in qi, and there can be functional changes in L because of functional changes of qi dot. So it's basically you have to write delta L in terms of the partial derivatives. So this will be nothing but, so I can write I equals 1 to n. Okay, so one point I forgot to mention is that it doesn't matter where I am writing this L. So I can write L also in terms of xi and xi dot, which is the Cartesian system. Okay, because it's a scalar function, it has a monogenic form. A scalar is a scalar in all coordinate systems. So which means at every point in qi dot space, it has this exact same value, one single same value. So whatever you derive in one coordinate system will be absolutely the same in all the other coordinate systems. So there is no problem in writing it down in a particular coordinate system anymore. Yeah, that's something that we wanted from the beginning, that physics should not be written in preferred coordinate systems, and that's kind of we are achieving here. Anyway, so this I'm writing in generalized coordinates. So it will be delta L delta qi, and then the functional change in qi plus, you should put the bracket here, delta L delta qi dot, functional change in qi dot. Right? So let us put this back into our Hamilton's principle. Hamilton's principle simply says that delta A equals to 0, which essentially tells you delta of t1 to t2 L dt equals to 0, which is integral of t1 to t2 delta of L dt. And now I can put delta of L from what we have just calculated. So we get t1 to t2 summation over I equals 1 to n delta L delta qi equals 0. Okay, and again I call this I1 and call this I2, and have a look at I2 first. Okay, I2. I1 is actually in the desired form already. I2 is, and I2 I will do a similar trick that I have done with one of the integral earlier. Okay, so again let me look at this quantity ddt of total time derivative of summation over I equals 1 to n del L del qi dot delta qi. And you know what I will do? I'll kill the first function first with the time derivative. So I'll get ddt of del L del qi dot, and then I get plus summation over I equals 1 to n del L del qi dot and delta qi. So I have to kill the second one. And you realize that, sorry, so the dot should be there. You realize that this or this is same as this. So again I can replace them. I can replace this with this minus that. And what happens to the first term? So the first term, when I put back into the integral, this is just t1 to t2 d of, see the dt and dt cancels out, d of I equals 1 to n del L del qi dot delta qi, and I can evaluate the integral. I can evaluate the integral immediately, which means that this just becomes this as t1 and t2. But you see that has this delta qi, which is the variation at the endpoints, which we said are 0. Remember that we said that the variation at the endpoint are 0. Configuration of the system is absolutely known. No variation at the endpoints. So, and hence this integral, now I can write down. So let me write it here. I2 is nothing but negative of the first integral, which is minus of summation over I equals 1 to n ddt of del L del Qi dot, and I should have the integral sign for the integral t1 to t2 dt. I missed a delta Qi here. So that's I2, and I had a I1. Now I1 has a delta Qi, I2 also has a delta Qi. So the entire thing now I can write as integral of t1 to t2 summation over I equals 1 to n ddt of del L del Qi dot minus del L del Qi delta Qi dt equals 0. So that's what Hamilton's principle gives us. So you see, this has the form as summation over I equals 1 to n some vector ai. So this is components of some type of vector in n-dimensional space. See, it has an index I, so there are n components times delta Qi, and that is the integrand, right? If this is 0, the integrand has to be 0, so this has to be 0. And then you argue, just like as we argued in the case of principle of virtual work, this has to be 0, so these are completely independent dimensions, one doesn't depend on the other, means that this ai has to be 0, independent, because these are independent. And then what do you get? You get ddt of del L del Qi dot minus del L del Qi equals 0. Remember that there are n equations, there are n such equations. These are your Euler-Lagrange equations. These are essentially Newton's second laws, but now you can write them in arbitrary coordinate system. And that's a very important understanding, that it not need to be even a generalized coordinate anymore. You start by writing L in any arbitrary coordinate system. In terms of those L, you will get these equations. So Euler-Lagrange equations, then you will get in any arbitrary coordinate system. In each and every coordinate system, the Euler-Lagrange equation will look different, but they will give rise to the same trajectory. The final trajectory will not change. Okay, so that's where I will stop today. So what we did today is, if you remember, so let me recapitulate what we did today. We started with the D'Alembert's principle, and using that, we kind of argued how to get the paths, how the D'Alembert's principle can be used, at least in our brain, to get the right trajectory. And then we said that, well, we cannot keep this in a monogenic form in terms of a scalar. But what Hamilton realized is that if I integrate it over that along the trajectory in between two times, that is supposed to be 0, and then I may be able to put it in a monogenic form. So we discussed a little bit of functional analysis, because that action that Hamilton defined is a mathematical tool, mathematical quantity which we call functional. I discussed a little bit of functional analysis, and then we explicitly showed that how, using the D'Alembert's principle for a simple case of a monogenic force, how we can write that integral in a monogenic form. And that monogenic form we wrote it in terms of a scalar, which gives you genesis of the trajectory. We call it the Lagrangian function, and we said it has all the information about the system. And then came the Hamilton's principle, where you elevate this to the following sense, that you say that given a system, first I write down the Lagrangian by whatever means I want. It's not always t minus v, it can be different for different systems, but I say that it will always be possible for me to write down the Lagrangian of the system. Well, that is not completely true, but we will see what are the caveats there. And it turns out that when you have more deep understanding of physics, there is actually no caveat. But anyway, so let me put it up to that in that point. So so to start with, I write down the Lagrangian of the system by whatever means I want, and then I integrate it between two fixed points in time. I get a number. I integrate it along a particular trajectory. I get a number. Now I say that I'll say this, the trajectory which is followed by the particle between the time t1 and t2 will be the trajectory that for which this number, which you call the action, will have a stationary value. Okay, so that is what is the Hamilton's principle. And then we saw explicitly that how from the Lagrangian one get the Euler-Lagrange equation of motion, which are a set of differential equations which are easy to handle to solve for the trajectory of a system. And we argued that it will be, you can start with any coordinate system now, not only generalized, but any coordinate systems, write down the Lagrangian in that coordinate system, work out the Euler-Lagrange equations of motion. If you have enough initial conditions, you should be able to solve for the dynamics of the system. You will get different equations, different type forms of differential equations if you choose different coordinate systems, but when you solve, you will get the same trajectory. Okay, so I will stop there today.